In this lesson, I'll show you how to express current in an RL series connected to an alternating voltage source. The question reads, a switch is closed at t is equal to 0, thus applying an alternating voltage of amplitude E to a resistor and an inductor in series. Write an expression for the current shown below. The first thing that we have to do to answer this question is refer back to Kirchhoff's voltage law, which states that the sum of the voltage that drops across a resistor R, an inductor L, and a capacitor C in an electrical circuit must be the same as the voltage source, EFT, applied to the RLC circuit. That being said, the voltage across this resistor can be represented using Ohm's law as resistance times the current. So we have R times the current, and the voltage here can be represented as the inductance L times di over dt. And this is equal to our voltage source, which is represented as E times sine omega t. E times sine omega t. Now, if I divide both sides of this equation by L and rearrange it, I'll end up with the following. Dividing this term by L, I end up with L over here. Dividing this term by L, this L goes away, and dividing this term by L, I end up with E over L times sine omega t. And if I place this term at the front and this term next to it, I'll end up with a first order linear differential equation. Take a look. Now, because this equation is a first order linear differential equation, you can identify your P and your Q term, where P and Q are functions of the independent variable, and in our case it's t. Therefore, in this particular equation, this right here is our P, and from that we can find an integrating factor that will enable us to find the general solution for this example. Now, we did something like this in question 1, so you can go back to it in full detail and see how we did it. So because this is our P, I'm going to substitute that into my formula here. My integrating factor is represented by the letter R. So let's go ahead and find out what our R is, because that will enable us to find the general solution. We have R is equal to e to the power of the integral of P, which in our case is R over L. Take a closer look. And over here we have dx, but our equation here is in terms of t, so we have dt instead. Both R and L are constants, so you can pull that out. And if you pull that out, you're taking the integral of dt, which is simply t. So we have e to the power of R over L t, and this is our R value. Now, what we do with the R value is multiply this whole equation by it. So technically I'm multiplying this side and this side by e R over LT. If I do that, I'll end up with the following equation. Now that I've written this down, what I'll do next is clear the dt's on the left side. So if I multiply this whole equation by dt, this thing, I'll end up with the following. dt multiplied to this side will get rid of this, and the dt over here will be distributed to this term, and you'll have a dt over here as well. So multiplying this side by dt, I end up with... The reason why we found our integrating factor R is because if I take the integral of the left side in its current state, I'll end up with the integrating factor R over LT, times the dependent variable on the left side, which happens to be the current. So I R over LT times I is actually the integral of the left side. The right side, on the other hand, stays the way it is. But we still need to integrate it, so I'll indicate that with an integral symbol. So we have the integral of E over L, our constant, which we'll pull out next, sine omega t, e to the power of R over L t dt. Like I mentioned, I'll pull out this E over L, and the left side stays the exact way it was. Having pulled that out, we have to take the integral of this expression. Now, to take the integral of this expression, you'll need to use integration by parts. So you'll need to choose an appropriate dv and an appropriate u value. The u will be differentiated and the dv will be integrated. Now, I do have a lot of content on integrating by parts, so I'm not going to go through the process with you, although I will tell you that this factor will be considered your u, And this factor will be considered your dV, along with this dt, which will enable you to integrate. Now, if you do integration by parts correctly, you should end up with the following expression, plus a constant k. So we have the following equation, and what we can do next to clean this up a little bit and simplify is divide both sides by e to the power of RT over L. If I do that, this will clear out on the left side, and on the right side, it will also clear out. And after some more manipulation, you should end up with a clean looking equation that looks like this. Plus k e to the power of negative RT over L. Notice that e to the power of negative RT over L would have been k over that expression, but we decided to put it in the numerator, and therefore the exponent became negative. So just keep that in mind. Now that we've simplified this equation to this point, if we use the impedance triangle, and it's shown on your screen right now, you would see that r squared plus omega squared L squared is actually equal to z squared, which is the square of the impedance. Furthermore, by Ohm's law for alternating current, E over Z is equal to the current I. And this gives us the amplitude of the current wave. Therefore, if I switch this now with Z squared, and I split it up so that I had current is equal to E over Z bracket R sine omega t over Z, pretend that it was 1z as the common denominator for this fraction, and we distributed the z to the two terms above, minus omega L cosine omega t over z plus our constant k times e to the power of negative RT over L. This now can be replaced with capital I, and I'll rewrite the rest. And then again from the impedance triangle, R over Z is equal to cosine phi, and omega L over Z is equal to sine phi, and I'll write that down for you, where we have R over Z is equal to cosine phi, and omega L over Z is equal to sine phi. Substituting these values into here will give me an identity known as the sine of the difference of two angles. That identity is also shown on your screen. Now, if you're confused, take a look at the equation with these substituted in, and it should look like this. And this is an identity which will be replaced with sine omega t minus phi times I, the one out here, plus k e to the power of negative RT over L. And this gives us our instantaneous current. At this point, we can find out what k is by substituting I is equal to 0 when t is equal to 0. Let's see what happens. Substituting t is equal to 0 into here, we end up with capital I sine negative phi plus k e to the power of a 0 here makes this whole thing 0. So we have e to the power of 0, which is 1. I've removed the e for convenience. Moving this k to the left side, we have negative k I times sine negative phi. Dividing both sides by negative 1 gives us k is equal to negative I times sine negative phi. And of course, instead of writing this negative out here in a negative angle, we can get rid of these because it's the same thing. And using the impedance triangle, which is shown on your screen again, sine phi is actually equal to x subscript L over Z. Therefore, k is equal to I times x subscript L over Z. What I'll do with this is substitute it into here, giving us the final formula, current is equal to, our current therefore has two parts. One, a steady state alternating current of magnitude I, and that's shown right here. And two, a transient current with an initial value of I times x subscript L over Z, which decays exponentially, and that's shown right here. And there you have it. That is how to express current in an RL series connected to an alternating voltage source.